Welcome to the internship program. I am Shubham Gupta from NextGen AI Frameworks Private Limited. I have more than 14 years of work experience in the fields of artificial intelligence, software development, and robotics. This video is part 2 for Generative Adversarial Network project. Let's continue. Okay, so let's see how this project works. I cannot run this project in this session. I tried running it and it took 1 or 2 hours to generate the output. So I have shown you the output. I tried running it in Google Colab, so you can also run this on your computer and see the output yourself. It was trained for 200 epochs. Okay, so let's look at the code, how it is working. So first of all, you will require a virtual environment and activate the virtual environment like this in Windows. And the libraries you will require: torch vision, numpy, matplotlib. Part comes for preparing the dataset. So if you pass the, you don't have to go to Google and search for the dataset. It will automatically be downloaded like this through torch vision. Import datasets, datasets.mnist, and you give the path and it will be stored in that particular path. So we will normalize the images to a range of this, as this helps in stabilizing GAN training. So normalize the images. So let's see step by step. I have mentioned more details line by line and each argument what they means. So transforms.compose, this function allows you to combine multiple transformations. So multiple transformations. Here we are applying two transformation. Transforms.toTensor, this one converts the image from PIL, Python imaging library format, to a PyTorch sensor. So as you know, we are dealing with images, but we cannot use directly the images to train the model, as I told you many times. So this time we are changing it to PyTorch tensor. It also scales the pixel values from the usual range to 0 to 255 down to 0.0 to 1.0 range. Transforms.normalize, what this means is this normalizes the pixel values of the image to the range. Here's how it works. So the first parameter specify the mean to subtract from each pixel. Second parameter the standard deviation. And normalizing the range is common to GANs because it helps stabilize training and makes the data more compatible with the certain neural network activations like TAN. So I will tell you more about this in this article. I have included this. So datasets.mnist, this function loads the mnist dataset from torch dataset library. This is simple to understand. And what this is doing is root like this, specify where to save or load the dataset. If it doesn't already exist in this location, it will be downloaded. So you can store the dataset at custom location like this. Train true indicates that we want the training portion of the mnist dataset, not the test portion. Training true, we need the test training portion. Transform, let's see more arguments. Transform applies the transformations we defined earlier, converting to a tensor and normalizing. And I told you why to create two tensor, because we will be training a neural network, and there you will require a tensor type data and not the direct image. So this is what this argument means. And the last one is download true, downloads the dataset if it is not already in the specified directory. This is the argument download_true. Then we have this one, data loader. This class wraps the dataset into an iterable, providing convenient ways to batch and shuffle the data for training. So train_dataset, batch size 64, shuffle true. So that what train_dataset, the dataset to load, here set the training portion of MNIST. Batch size 64 specifies the number of images per batch, allowing the model to process multiple images at once. So if you go one by one, and if you have 10,000 images, so you can understand the time it will take. So instead of that, you can use batch size and increase or decrease the batch size as per the requirement. Batch size of 64 is often a good balance between memory usage and training stability. And shuffled equals to true. Shuffle the dataset at each epoch to ensure the model doesn't see the images in the same order each time. We can improve generalization. So as you understand, if you have images like 1 2 3 4 5 6 like this, so each time you pass in each epoch 1 to 10, so this makes no sense. So it will shuffle just like you shuffle the cards. It will shuffle the images, so that each time in the each epoch it will see the images in a different perspective. So first image will become something like a third image, like this. So it will shuffle the sequence of the images. This is what shuffle equals to true is. So this is the from the data loader. This is how I called here: batch size, shuffle, and train dataset. Define the generator and discriminator models. So as I told you, two type of neural networks will be included here. One is generator and one is discriminator. And I told you the concept, what they means. So generator will create similar images to those on the in the training data, and discriminator evaluates the authenticity of images, real or generated. This was the basic concept, and this is the code for discriminator and generator. So let's see what they mean here. So the generator takes a random noise vector as input and transform it to 228 by 28 image that resembles an MNIST digit. So as you know, it will not be computing the images directly. It will be working on the tensors. So it should be what will happen is the generator takes a random noise vector as input and transform it to a 28 by 28 image that resembles an MNIST digit. So breakdown of generator layers, let's see. Okay, so latent dim. Okay, so here you can see the hyperparameters. So what they mean, let's see the size of the input noise vector. Latent dim, the size of the input noise vector, example 100. This is the seed for generating images. So seed, starting point. Linear layers, each layer successively transform the noise into higher dimensional feature spaces to create a structured high dimensional output that resembles an image. Then comes the activation functions, introduce non-linearity, helping the network learn complex patterns. And we have used this activation function in previous projects also. So let's see linear versus non-linear transformations. I have included this specific thing so that you will understand why I am using the particular activation functions. Okay, so linear versus non-linear. Without activation functions, each layer in a neural network would just apply a linear transformation, that is matrix multiplication, to the input. Stacking linear transformation results in a single equivalent linear transformation. The limits of this limits the network ability to learn anything complex because all it can represent is a straight line or a flat plane of prediction. So all it can see the flat line if you don't apply the activation function. So to introduce non-linearity and create a data structure that can understand more complex things, you will require activation function. So you can see here activation functions. Okay, and then comes the batch norm. Batch norm, what this is and why I'm using is stabilizes training by normalizing the input to each layer, reducing internal shift, and batch norm helps the generator produce more consistent outputs across training batches. Look at these lines, produce more consistent outputs across training batches, consistent, aiding in realistic image generation and reducing the risk of instability that often plagues GAN training. This standardization is applied to mini batches of data during training, hence the name batch normalization. Because it is working in batches, this normalization is or standardization is working in batches. This is the reason it is called batch norm. TAN activation. Then what we have here is the output layer uses this to scale the output to a range of this, matching the normalized range of images. Activation function is used in the output layer of the generator to scale its output to range this, and shows that the generated images have pixel values in a similar range as the real image, helping the discriminator more effectively distinguish between real and fake image. So in simple words, you have to create realistic images. So for that reason this activation is being used. And I have I think mentioned more things okay in the article. So let's see this discriminator model. So this one is generator model generating the images, and now we have the discriminator model. As you can see here, sequential. So sequential means layer by layer, as you know. So in the discriminator, let's see what we have. Do you have any doubt understanding the generator? Okay, so discriminator, what this is doing is is a binary classifier that takes an image, real or generated, and outputs a probability indicating whether the image is real or fake. This is what discriminator is doing. Either the image will be real or either it will be fake. So input layer accepts a 784 dimensional vector, flattened 28 by 28 images. This is what it takes. And leaky ReLU activations allows a small non-zero gradient when the input is negative, which helps prevent dying neurons. So there is a problem of dying neuron. So I have mentioned some details about it here. Allows a small non-gradient when the input is negative, which helps prevent dying neuron. In a standard ReLU activation, any negative input is set to 0. This is what happens in ReLU activation, which results in a gradient of 0 for that neuron. If the neuron consistently receives negative inputs, it can die. Because it stops learning entirely, its gradient is 0. This is the problem. So leaky ReLU addresses this by allowing a small gradient, usually around 0.01 times the input, for negative inputs instead of 0. So it will be focusing on this small decimal digits. So this small slope keeps neuron alive even if they receive mostly negative values, ensure they can still contribute to the learning. So this is the thing, this leaky ReLU. This is the difference between ReLU and leaky. It will keep the small gradient, usually around 0.01 times the input, for negative inputs instead of 0. And in ReLU we have 0 or 1, and if the neuron dies, it will not contribute to the learning. But if we want to keep them alive, we can use leaky ReLU. Then we have a sigmoid activation. What this means is, to produce values between 0 and 1, we will require this activation, representing the probability that the input image is real. It squashes any input to a range of 0 to 1, which is well suited for binary classification tasks like those GANs where the discriminator needs to classify images as real or fake. Now I have mentioned here, you will say that ReLU is also doing same thing, 0 1. So why we use sigmoid activation here? So I have mentioned this here. Sigmoid is preferred over ReLU for several reasons, mainly because sigmoid is a designed to handle binary classification type. RL is generally suited for, look at this, it is generally suited for hidden layers in neural network rather than output layers. Here we are dealing with output, and in whenever I implement this is for hidden layers. This is the difference, and this is the reason I am using this in the output. So if you see here, this is the last layer. So in the last layer I am using, but in the hidden or middle layers I am using the key ReLU. So this is the difference. I have mentioned everything in these articles, I think minute details also. So training the GAN, the training process alternates between updating and balance the GAN. Okay, so this will be the code, this for loop, and this will be the code. I told you the basic. Now comes the part of integrating it in the for loop and training process. So latent underscore dim, I will show you the code here. And what this to device means, you can understand this. If you have a GPU and you are running your project on GPU, so the dot to device will use the GPU instead of CPU for the training process. This is what dot to device is. Okay, so hyperparameter, number of epochs, I think I have mentioned these, yes, here. So latent dim, number of epochs, batch size, I think I have told some things earlier. So let's see, latent dim is the length of the random vector input to the generator. Number of epochs specify how many complete passes through the training data. The more epochs, the better will be the model. So the training rate is the step size used by the optimizer for updating weights and device, ensures the training can be performed by the GPU if available for faster computation. Generator and discriminator are initialized and moved to the specified device. Binary cross entropy loss is used to measure the discrepancy between predicted and actual labels, and you know what predicted is and what actual labels, what should be the final output, is it near to the final output or not. So this is the thing, helping the models learn. Adam optimizer with the given learning rate is used for both the generator and discriminator, providing smooth and effective weight updates. And training loop, the main training loop runs for num epochs. Each epoch involves iterating over the images in the train underscore loader batch by batch. And if I look at the code, you can see it is running on epoch, number of epochs 200 times, so it will run 200 times. And valid and fake are ground truth labels. So where are valid and fake? These are the ground truth variables or labels used to calculate the BCE loss for real and fake images respectively. Real images are labeled as 1, fake images are labeled as 0. Okay, so remember this, in this project real images are labeled as 1, fake are labeled as 0. Then we have the train the generator part. So generate a batch of random noise vector Z and use generator to create images, gen underscore images. Let's see, okay, generated images, assuming they are okay. So pass the generated images through discriminator and calculate the loss, assuming they are real. The goal is to fool the discriminator into thinking generated images are real. So this is the discriminator, we are passing these generated images. Okay, and back propagate and update the generator's weight to minimize G loss. So to reduce the loss, we are working on it. So train the discriminator, calculate real underscore loss by passing actual images through discriminator and comparing the output to valid labels. Where are the valid labels? Here, see. Okay, so this was the real loss and this is the fake loss. We are calculating two things here. So this is this real loss by passing the actual images, and this fake loss is by passing the generated images through discriminator with the label fake, and here you are giving the valid labels. So there are two types of labels available. You are checking both things, real loss and fake loss here. and average the loss to get a D-loss. So how we are getting the D-loss, and I think this is the final output that I was getting. See D-loss. How are you getting the D-loss? Average the losses. So then back propagate and update the discriminator way to better distinguish real from fake images. So it will go on and on until the model is perfect. After each epoch, print the discriminator and generator losses, providing insight into how well each model is learning over time. And then the part comes of saving the images. There is a separate function here for generating the images. Okay, and output path is this one, and it will generate the image and save the output. So this is the part of rescaling the images, numpy part, and computation part, and then image from array. So from the computations and the numerical data, if you want to convert the image, you can convert like this and save the output like this. So this is the save generated images part is very easy. So the main purpose of this project was to tell you how generative or GAN is working in the market. I told you the basic and created a project for generative adversarial network, and this was the content for week 10. I already covered the week 9 content, and from the week 10 I told you about GANs. This video marks the completion of this project. I will see you in next video. Have a nice day.